Okay, welcome back. This is video 3 for the drivetrain design unit. This video may turn a little long, and for that I apologize. Okay, so one of the major attributes when we talk about the drivetrain's performance is how well it turns. And there are going to be two main properties. We've got the turning torque and the turning scrub, which this is torque also. We can think of this as being torque from the motor, and this is being torque from friction. So turning torque is the torque about the turning point which causes the robot to turn. Turning scrub is the friction which resists the robot turning. It's caused by the wheels dragging sideways on the ground as the robot turns. It resists the motion to turn. So again, turning scrub can also be talked about in terms of torque. Okay, so if we look at a typical skid steer drivetrain, especially ones where all the wheels are drive wheels, all of the wheels will exert a force that contribute to the turning torque, but they will also all drag sideways, contributing to the scrub. Now, let's look at this diagram to help us visualize. Now, this is not a real drivetrain. You would have to be really silly to try to build this. But it helps as a good example for scrub and torque. So in this fake drivetrain, we've got two drive wheels, right here, right here. So notice how, because of the torque, we have a force going this way, and we have a force going this way. And our turning point is right here in the center. So we've got this turning torque in the center. But at the same time as that's going on, these wheels would exert a kinetic friction here and here because they're being dragged. And that makes a second torque, a torque due to scrub. It's a negative torque. So we have these competing torques. We have this positive torque that is trying to turn it, and we have the negative torque from scrub that's trying to prevent it from being turned. Now, as long as the turning torque is greater than the turning scrub, the robot will be able to turn. But if the friction becomes too great, we can lose a lot of energy. Remember, friction converts mechanical energy into heat. So if there's too much friction, we will lose a lot of our mechanical energy. So in a more traditional drivetrain, we would have this. And in this one, we have our forces. So these are the positive forces. These are the good ones. These are the ones trying to turn your robot. But we also have our friction. These are the negative ones. These are the ones that we want to try to reduce as much as possible. All right, so that's what we have right here. So in turning torque and turning scrub, they're both torques about the turning point. A torque is a turning force. We've got a linear force times a distance. Remember that torque, the way we calculate torque, is a force times a lever arm distance, and that the force must be perpendicular to the lever arm distance. So down here let's take a look at a more detailed picture here. So here we have our positive torque. So the robot's trying to turn counterclockwise. So here we have our force from the motors, and then this distance right here is our distance, our lever arm distance. It's called x here. So this torque would equal this force times x. Notice that they're nice and perpendicular. So up here then, that X can be found here and here. For the scrub, again, that's where the wheel is being dragged from kinetic friction. And then this right here is our value. In this diagram, it's called Y. So for the scrub, it would be a force times a Y. And it's an opposing torque. So up here, that would be your value for Y. Now, if a drivetrain has multiple wheels on the ground, all of these wheels will contribute based on their location to the drivetrain relative to the turning point. So, how can we reduce turning scrub? Well, we can choose different wheels. So we can try to choose low friction wheels. We could make our Y smaller. Or, if that's not an option, make the X bigger. If we make the X bigger, we are having more torque devoted to turning, which can overcome our scrub. Now, a last option, though, is use your omnidirectional wheels. Omnidirectional wheels have zero turning scrub because they have those special wheels inside that are dedicated to moving sideways. Now, we can have a hybrid drivetrain where we have high traction and omnis. And what's kind of cool about this is that it changes where the turning point is. The turning point will go to where the high traction wheels are. So if we have omnis in the back, the turning point goes to the front. If we put our omnis in the front and high traction in the back, the turning point migrates to the back. All right, so let's wrap it all up. Let's take a look at a couple designs here. Here we have a long, narrow chassis. And this is actually really, really bad. This has a low turning torque, and that's because X is small. And we have a high scrub, and that's because Y is large. So this is a bad design if you're going to use all high traction wheels. Over here, we have a good design. Because for this one, we have a wide maybe short's not the best word, but I'll go with it. A wide short robot. This one has a high turning torque. And that's because X is large. And it has low scrub. And that's because Y is small. So if you need to pause the video and kind of think about, torque. And remember, torque is defined as a force times a lever arm distance, a force that's perpendicular to the lever arm distance. And it should make sense why the long, narrow chassis would have a lot of scrub with low turning torque, and the wide, short chassis would have a large amount of turning torque with a small amount of scrub. And, just by making subtle changes, we can change the dynamics of these systems. Also, our turning point, we can move the turning point around by simply adjusting where we place an omnidirectional wheel. And the rest of this narrative here, I'll let you read on your own. Too far. Okay. Now to kind of wrap this up, let's talk about some gear train design. Our gear train is responsible for delivering the motor's power to the wheels. And so far this school year, we've already talked about compound and non-compound gear trains and how to calculate the mechanical advantage of them. So here we want to start wrapping things up and talking about wheel speed. How fast are those wheels moving? So the first thing we want to do is, we need to know how fast the robot's going to move across the field. And we need to know that based off of how fast the wheels are spinning. So for each time the wheel makes a full rotation, we need to understand that it's going to roll forward a distance that's equal to the circumference. And that's what this picture right here is illustrating. That as the wheel makes one full rotation, the distance, the rolling distance, is equal to the circumference of the wheel. So by calculating the circumference of the wheel, we can figure out how far it goes when it has one rotation. Now, circumference equals pi times diameter. And for the 4-inch wheels, the diameter is 101.6 millimeters. And for the 2.75-inch wheels, that's the small green ones, it's 69.85 millimeters. So if we want to know how far does the wheel travel for one rotation, well, for the 4-inch wheel, the circumference equals pi times diameter. So that would equal pi times 101.6 millimeters. So the distance would equal 319.02 millimeters. We can convert this into centimeters. This would be the same thing as 3.19 centimeters. Okay, let's say that those 4-inch wheels are attached to a motor that spins at 100 RPMs. What will be the robot's linear speed? Okay, well, linear speed equals r times omega. So the radius of these wheels, if it's 101 millimeter, if we cut that in half, it would be 50.8, I believe, millimeters. In fact, let me pull out my calculator and check that real quick here. Yep, 50.8 millimeters. So that's our radius. Now we need to figure out our omega. Now this omega has to be in radians per second. So if we have 100 revolutions per minute, 1 revolution equals 2 pi radians, and 1 minute equals 60 seconds. So 100 RPMs equals 10.47 radians per second. So this linear speed then would be 531.97 millimeters per second. Or, if you would prefer to have in meters per second, this would be the same thing as 0.531 meters per second, or 5.31 centimeters per second. All right, so what mechanical advantage will be needed to make this robot's wheel spin at 350 RPMs? Well, remember that the output rotational speed equals the input rotational speed divided by mechanical advantage. So, mechanical advantage then would equal the input rotational speed divided by the output rotational speed. So that'd be 100 RPMs over 350 RPMs. And I get a mechanical advantage of right around 0.286. And then you would have to choose the correct gear configuration to make that happen. All right, well, that concludes this unit's worth of notes.